Okay, so what we did so far is we have this almost harmonic, and now I want to show you how to construct the almost harmonic, or I will show you today and tomorrow how to construct the almost harmonic cocycles, okay? Simply, at least in the amenable case. Remember, I told you that at the end of the day we're going to do the amenable setting, and I'll show you exactly where you use amenable and why it's good enough to do is amenable, because at the end we need this for groups of polynomial growth. So why groups of sub-exponential growth are enough to get amenable, but we haven't talked about that yet. But let me just show you a consequence. So theorem, and this is the original theorem. What did we sorry. Okay, so let's not do theorem yet. We need some more constructions. Okay, so assume. So let f be a L2 function of my group. Okay. And now I'm going to define, and let's assume some stuff. Okay, so
let's some R measure in the different or not necessarily.
Har measure? It's a countable group, so the Har measure is just the counting measure. Okay, so assume that we have some L2 function. Okay, and now what we want is so first of all, what is f check? F check is a function which is defined to be at x. It's just defined to be f of x minus 1. This is just to reverse the direction of the elements. Okay, and we're going to define. I'm going to define a function from G into L2 of G, okay, by the co-boundary.
This is we're doing continuous proof, or we start something?
I'm showing you the construction of how to get almost harmonic cocycles. Okay? So for a given f, I'm defining C. C is actually CF, right? It depends on f, okay? On my specific f, okay? Then we'll take a sequence of f's, we'll get a sequence of c's. Okay? Let's now compute what does
Everything on f is like the regular left action on the
So x acting on any function phi at the point y is phi of x minus 1y. That's all. Okay? This is a regular representation, exactly. So G acts on L2 of G. It's a regular representation. Okay? So the almost harmonic cocycles will start from the regular representation, which was the representation we started with, but we'll end up with a different representation, which is weird and abstract. Okay? So now, let's compute. First of all, we want these to be cocycles. Are they cocycles? So I already gave you this exercise. CF is a cocycle. Right? It's very easy to see. Any coboundary is a cocycle. Okay? Just compute this. Okay? Because this is the way you define it. You take the action, you act, and you shift, and you always get a cocycle. But what about the average here? Okay, so again, mu is going to be finite first moment, so that this converges absolutely. For cocycles, things, right, converge absolutely as soon as you have first moment. So what about this average? Okay, so let's compute this average. This is what? This is a function in L2, right? This is a function in L2.
Wait, do we define C or CF or?
C is CF. C is CF. We have a fixed F now. Okay. Okay. So what is? No, sorry, not the norm. This is an L2 function, right? So I want to compute what this L2 function is at the point y. Okay? So what is it? Let's write it down. It's the sum over all x, mu of x. We have the function x f check minus f check acting on the point y. Right? This is the definition. This is equal to, now what is fx f check at the point y? It's f check at x minus 1 y. But that's just f at y minus 1 x. And this will just be y minus 1. So we have sum over x, mu of x, f at y minus 1 x minus f at y minus 1. I hope you recognize this. What is this? This is the average around y minus 1. And this is the f at y minus 1. So this is just minus the Laplacian with respect to mu, right? The Laplacian is I minus the average. So this is the average minus I. So this is minus the Laplacian of f at the point y minus 1, right? Okay? So this is a very nice relationship between the co-boundaries, the averages of the co-boundaries, and the functions. So what we get is that the average of the co-boundary around 1 is exactly something to do with the Laplacian, or we can write it differently. This L2, this is the co-boundary. The co-boundary is just, I said, any cocycle of this form is called a co-boundary. You take a vector, you act on it, and you move. Okay? So anyway, these special cocycles, if you average, so this is an L2 function. As an L2 function, it's equal to this L2 function. This, and you put a check here on everything, right? Because it's y minus 1. This at the point y is equal to this at the point y. Okay? So that's one thing. So of course the norm of these things, remember at the end we're going to have a sequence of these things. The norm is going to go to 0 if the norm of the Laplacian, check doesn't do anything to the norm, minus doesn't do anything to the norm. So if we can find functions f whose Laplacian goes to 0. Okay, in norm. The norm of the Laplacian. Yeah, so almost harmonic functions, L2 functions. Okay? Now, on the other hand, I want to check what is this. Why do I want to do it? Because I see into the future, and you guys don't, but so I want to check what this is. Sum of the square of the norms of the CX's. These are L2, CX is an L2 function. I can take its norm, right, in L2. Right? If you want, what I wrote here is just the expectation of C of x1 in norm squared. Right, do you agree? If I take norm squared of the C of x1, that's a random variable, and I get... okay, what is this? Well, okay, outside I have sum mu of x. By the way, for this to converge, what do I need? For this to converge, this is going to be infinite, or it's not guaranteed to be finite unless I have mu with second moment, right? Because this is bounded by an x squared. Okay? So I'm going to assume that mu has second moment. Okay? So the expectation of the sum of the norm squared, this is sum x, mu of x, then I have to develop the norm squared. So I have to sum over y, right? And I take the function c of x. So what is c of x? Let's already write it down. It's x f check minus f check. All of this at the point y, absolute value squared. Right? That's how you do a norm. You sum the square of the absolute values. Okay? But what is written inside this thing? Again, this is f of y minus 1 x minus f of y minus 1, just like we did before. Right? So if I sum all of these, I get sum over x, sum over y, mu of x. Now when I sum over all y, I can change y inverse to y, right? I mean, it's going over the same, I can do the change of variables one over side, then I get f of yx minus f of y squared. What is this? Do you recognize it?
Called there was the Laplacian and the other, the divergent.
Well, so okay, so let me write it again. Let me write it in a slightly different form, and you'll notice it. This is the sum over all possible x and y, right? Mu of x. So and instead of so it's the sum over all y and all z. Okay. Now z is going to be yx. So instead of going over all, once you go over all y, you can go over all z, right? Instead of writing mu of x, I'm going to write the conductance of yz. That's good, right? Because if z is yx, then that's the conductance of yx, right? It's just mu of x, right? And then I have the difference between f of z minus f of y squared.
We already have C.
Yeah, okay. Let's see mu. Okay? Okay? So what this thing is, I just wanted to put it in the form that reminds you, right? This is exactly, okay, instead of writing the C, I'm going to write P. P mu, right? Because the total conductance coming out of a guy is 1, right, on the network. So this mu of x is just, what is this, right? This is right, you go over all the y's, then you go over all the neighbors with their probabilities, right? And instead of writing yx, I wrote z. Okay, so this thing is just, well, yeah, so this is the Markov chain with the p. And if you remember, this exactly was the integration by parts. This exactly was the integration by parts formula. This exactly was writing, if I wrote this was exactly the gradient of f with the gradient of f, which was the same thing as, and this is what I want to write here, up here, it was Laplacian, 2 times Laplacian ff, because Laplacian is half, when you move this you get divergence gradient is 2 times the Laplacian. Okay? So you can just work this out, just as matrices. You can just work this out. If you have a Markov matrix and you write Laplacian ff, you get this, so Laplacian is I minus p. Okay, I mean, just open up all the squares. You need to assume that everything converges absolutely so that you can put the sums, but that follows from the fact that we took mu in SAG2. Okay?
What happens if you use the fact that the adjoint of the gradient is the
Sorry?
The adjoint of the Laplacian is the factor.
Yeah, the adjoint operator for we said when you move this here, you get the divergence of the gradient, and that's what we define to be twice the Laplacian. But you can just do it directly. You can just do it directly if you want to compute it this way. Okay, I just wanted to remind you that you should notice that when you sum the gradient squared, you're actually getting exactly something that has to do with the this Dirichlet energy. This is Dirichlet energy. Okay? So you see the average of the norms is this thing. So if I can find a sequence of functions, so if, suppose I had the following thing, right? Suppose I had a sequence of functions fn in L2 so that their Laplacian goes to 0 and their Dirichlet energy stays fixed. Maybe it's 1. Right? Suppose I could find a sequence like this. Right? Then what do I have? Then if I define Cn x to be x fn check minus fn check, right? Then what I get is uniformly Lipschitz cocycles, okay? Right? Which are almost harmonic, right? The sum mu x Cn x, this is what we said, this is the norm of Laplacian fn, which goes to 0, right? That's the first one here. So this gives the almost harmonicity. Uniform Lipschitz is just because they're all cocycles, right? So they're uniformly Lipschitz. And two, I want to say that they're non-trivial, okay? In the following sense, oh, we didn't even say, remember the C of x's was the un of Cn and the limit. So this tells us that Cn, that C of x in norm is always at least the lim inf of the UNCN, which is just the lim inf of the Cn. So that shows that it's a non-trivial cocycle.
It shows the x1 to be the one that...
Yeah, but we can choose the next one, but you can even do without an x1, because we'll see that in our situation, what's going to happen here is that the sum x mu x Cn x in norm squared, this is going to be 2 for every n. And this follows from this guy. Okay? So you don't even need that lim sup. You just get that one of these guys has to be bounded away from 0. Okay? And so its lim inf is bounded away from 0. Okay? Right? It's impossible that all the x's here in this thing, here they converge to 0, right? Because you have an average, which is 2. Fixed number, right? Just take for every n, take an x in the support of mu for which this is maximal, and
don't need a check in the first one?
you do, but the norm of a check of the function is the same thing,
But they
right?
correlate because you said limit, but maybe like one time this is like 0.
Yeah, okay, you need to be careful. Suppose mu has finite support, that will work, right?
Okay.
At the end of the day, look, we have a choice of which mu we can take. But if you don't like that, you do the x1 trick. You make, right? There is one so that infinitely many times, this will be, so you can take a lim sup. Right? I mean, you cannot have this average staying 2 if they all have lim sup is 0. Okay? Think about it. Okay.
But it's bounded by the sum of the lim sup, the lim sup.
Well, okay, let's think about it. But we'll see. Okay. So the goal now, what is the goal? What do we want to do? We want to find the functions with that property, right? So the goal.
Can you remind me where we're standing? The left theorem we proved like for the most abstract, if you have a G action and then you have almost contact.
Yeah. So we're trying to. The goal of this thing is to prove the following theorem that I stated: if G is amenable, finitely generated amenable group, okay, and mu is SAG. Now I'm a bit worried because I need SAG2 for this to.
Maybe you wrote to.
No, it's enough for G to be. Okay, what I did here, the calculation I did here shows that this actually converges. Okay?
Yeah.
I mean, I took a function for such that this converges, and this is exactly equal to this. Okay, so I mean, that thing is defined. It could be infinite, but it's not infinite. It happens to be finite. Okay, so if G is amenable, mu is in SAG1, and then there exists a representation. From G into the unitary operators of some Hilbert space. This Hilbert space is separable. In fact, it's just L2 of G with a different unitary action. Okay? And a harmonic, mu harmonic, rho cocycle. Right? Cocycle with respect to. Okay? So we can find the root harmonic rho cocycle. Now, how do we prove this theorem? So the theorem will follow from if we find that if G is amenable and mu is in SAG1, then there exists a sequence of functions Fn inside L2 of G such that Laplacian Fn is always one, doesn't matter, it just has to be bounded away from 0, right? And Laplacian Fn converges to 0. Right? If I find these, then I do the co-boundary trick. Right? So this is what we just showed. We proved that this theorem implies this theorem. Okay? So now the goal is to find such functions in the amenable case. I didn't tell you what amenable is, but I'm soon going to tell you what amenable is and why it helps me to find such functions. And specifically, it's sufficient to find some functions phi n in L2 such that if I take the Laplacian of phi n norm squared divided by Laplacian phi n, okay, then this thing converges to 0 as n goes to infinity. Why? Because then, so why is this sufficient? I'm going to write down why this is sufficient. If you found a sequence of functions in L2 such that this ratio happens, I put a square here, it's important this square, okay? I want you to notice that this thing is homogeneous. Multiply phi n by a constant, you get squared upstairs, squared downstairs, so it's homogeneous, okay? And the thing is that you define Fn for this thing, right? You just define it to be phi n divided by the square root of Laplacian phi n. Of course, when I'm dividing by this thing, I mean that I found phi n's for which this is not 0. Otherwise, what I wrote here is not defined. But, okay? This is always a non-negative thing. This is just the Dirichlet energy, right? I can take its square root. And I can define Fn to be this function divided by this. And then you see that I have exactly this constant will exactly turn these guys to 1. Right? Because it comes out squared and you get Laplacian phi n divided by Laplacian phi n, it's 1. And this will go to 0 because you get exactly that term which was assumed to go to 0. Okay? So it's enough to find a function. Let's write it a bit differently. It's enough to...
This is the usual notation of inner product is concrete and inner product, right?
This is an inner product.
But then out can the norm of Fn goes to 0, but these are always equal to 1, like Schwartz says to go to 0.
No, the norm of the Laplacian of Fn goes to 0. That's not the same thing as Fn going to 0.
No, I'm not saying that Fn goes to 0, but if you look at the inner product and use Schwartz, aren't you supposed to? Oh, but maybe Fn is balances.
I don't see why.
No, it's fine. I think Fn balances. Because the right hand side.
I didn't promise you that Fn has norm 1.
Yes. I'm saying this thing
It must be like some guy said that it's
right. The norm of Fn must go to infinity, or at least not be bounded. Right? Because like uniformly bounded.
Yep.
Oh.
It cannot be uniform.
Yes.
Yeah. This rescaling, you see, what's going to happen is we're going to find functions for which this thing is going to grow. This thing is going to... so the norm of Fn cannot be bounded. Yeah, so this thing is going to shrink faster than this grows. Okay, so It's not going to scale it properly. Okay, I didn't scale the FNs to have norm 1 exactly. Okay, good. So how are we going to find this Fn? So here I'm going to do it very quickly for you. Okay, I'm going to do it easily. So what is an amenable group? Definition. A group G is amenable if the infimum over going to write the following fact. Okay, so what you want to do is you want to take the infimum over finite sets in your group of something. Of what? I want to take the infimum over the probability, so there is going to be a mu involved. Okay, there's going to be a random walk involved, symmetric random walk. So if there exists mu in SAG1, let's say, it's not so important, but it just needs to be symmetric and adapted. Okay. Such that when you take the infimum over f of what? Of the probability to escape f. So I want the probability that x1 is not in f. But now you have to ask me, how did you start? How did you start? Right? Okay? So you start uniformly on the set f. And then you ask in one step to exit f. It's in some sense a boundary term of f. If you think about simple random walk on a graph, you start uniformly in a set and you take one step. So it's exactly the number of edges, right? Or the weighted number of edges that exit the set. Okay? So when you start uniformly, I can do it this way. Sum over all the x's in f and take 1 over f. Right? So I have this quantity. Okay? This is a boundary term. This is comparing the boundary size to the volume. In some sense, this compares the boundary to the volume. You have to remember this. Amenable groups are those for which you can find bigger and bigger sets. Sets with bigger and bigger volume so that their boundary grows not as fast as the volume does. So if this is 0, okay? By the way, this is usually called the Chigger constant. Sometimes it's big phi mu, denoted big phi. So if the Chigger constant is 0, okay, then you say the group is amenable. Okay, now it's an exercise. This, of course, will change if you change mu. This number might change for different groups, will change if you change mu. It's an exercise to show that phi mu is 0 if and only if phi nu is 0 for any mu nu, say, symmetric adapted G1. In fact, it's just any symmetric adapted. You cannot change it without. Okay?
If you find one probability measure, then for all probability measures.
Yes, yes. But with different, for fixed f, this changes. If I change the random walk, imagine a random walk which takes only neighbor steps, and then you have one with big jumps. Of course, the one with big jumps has more probability of exiting maybe this finite set f. But for a bigger set f, it will, you'll still be able to, because you can take bigger and bigger sets that this goes to 0, then the other one will also be 0. You have to prove that this is the case. Okay? So amenability doesn't depend on the choice of random walk. Okay? Good. So now, how will we define our approximate harmonic functions, right? So assume, so this is some discussion, okay? G is amenable. Okay? By the way, a sequence like this, let me write this here. A sequence, so this is called Fellner's condition for amenability. There are about 15 million different conditions for amenability. This is called Fellner's condition, and in fact, he didn't do it with random walks, he did it with graphs. So the boundary of a set with respect to its volume. But that's up to constants. This is, if you take a simple random walk on a graph, this is just the size of the boundary divided by the size of the set, okay? And this is just the generalization to probability measures instead of to non-finitely supported random walks.
Is there a definition of amenability that does not refer to any other properties like actions or random walks or graphs? Like,
I don't understand what you mean.
Like you look at the group and you know if it's amenable or not without going to like if you can paradoxically split.
Yeah. I mean, there are millions of definitions, but they all involve, in a sense, some kind of representation. So I think, maybe not. Maybe there is some like, your question is fuzzy, so I don't know how to answer it, but okay. A sequence, I mean, if they're equivalent at the end of the day, they involve, for me, this is the simplest definition to think about. There's also Keston's criteria, but I won't discuss it now. So a group is amenable if and only if for every random walk, for some or for every random walk, okay, it's equivalent, the probability of return to the origin decays exponentially. That's a non-amenable. Non-amenable if the probability decays very, very fast.
Is it equivalent to non-amenable?
To non-amenable, yes. Okay, so that's another condition that uses random walks. But why do they? If we have time, we'll see. We can prove it. It's not very difficult. Okay, but for us, this is what I want to me. I want a group. Instead of amenable, I could have just said I want a group where I can find larger and larger sets that have small boundary compared to their volume, and a sequence Fn of finite sets such that this quantity 1 over Fn summing over x in Fn, probability starting at x that x1 is not in Fn, converges to 0, right, is called the Fellner sequence. Fellner is like this. Fellner sequence. Because Fellner was the one who introduced this condition. At the end of the 50s, 58 or 9. Okay? So if you take a Fellner sequence in a group, okay, assume G is amenable, and take Fn to be a Fellner sequence. We'll show soon that groups of sub-exponential growth are amenable. In fact, if you have non-amenable group, if a group is non-amenable, right, this means that there is some constant bounding the size of the boundary of every set from below by the volume. So this means the ball have to grow exponentially. So that's very easy. It's a very easy exercise to show that sub-exponential groups are amenable. But there are of course exponential groups which are amenable. Okay, so it's not at all a measure of growth amenable. It just
It's like the Goldchuk groups.
Goldchuk groups are all amenable. Yes.
Yeah, but it was an example of a group with.
No, that was an example of a group which is not elementary amenable. Okay, because elementary amenable groups have a dichotomy. They have to be. They don't have intermediate growth. Okay. Okay, so assume G is an amenable group and Fn is a Fellner sequence, meaning a sequence with that property that those things go to 0. Okay, let's consider. I'm going to change a bit notation because these fn's before, what I'm calling fn now is not what I meant, what I called fn before, okay? Just because somehow I'm used to it in my head. So fn, I'm going to define this to be, okay, just the indicator of fn. So this lives in L0. This is finitely supported, right? These are finite sets. Okay? Then I'm going to define psi n. I'm going to define psi n to be G acting on Fn. So remember, what is G? G is the green function. So it's a matrix which says right, it just counts the expected number of visits to y starting from x. Remember? Okay? Good. And now,
How does it X on a function?
what?
As a vector.
Yeah, so this is a matrix and it acts on a vector by summing. Okay? So, okay, let's compute what actually does psi n of x say. So this is sum over all y, g x y fn of y. But what is fn of y? It's just the indicator function of f, right? So this is the same as summing over all y in f, the green function starting at x, y, which I can also abbreviate by gxf. So this is
What is F?
fn. Fn is my nth set in my Feller sets. Okay? So what I can see here is that this is just, what is this? This is the expected number of visits to the set f, the expected number of time I spend in the set fn, starting from x. Okay, so this is expected starting from x, time random walk spends in fn. Let's look at the infinite random walk, count how many times it was in fn, and take the expected value of that. Okay, so this is what psi nx is measuring. Now, what you need to note is that, so if you do the expected number of visits starting at x to a point y, okay, well, what is that? Well, suppose y is equal to x, then you get one visit from time 0, then you take a random step and you start counting again because of the Markov property, right? If y is not equal to x, then you take one random step and start counting from that, and you don't have anything at 0. So this is exactly delta x of y plus, or sorry, delta y of x, I want it as a function of x, delta y of x plus the average of, right, the average of g to visit y. So yeah, so this means I average over this coordinate, right, over the starting coordinate, and I average it and I take this thing at the point x. Okay, that's just a Markov property. What?
What's the definition of premium of G?
Yeah, okay, so let's write this out very, right? So I get 1 if I was at x, and 0 otherwise, and then I have to do one step. So what does it do one step? I sum over all possible z, I go from x to z, and then I count the number of visits to y starting at z. Okay, so this is the precise, right? That's just a Markov property. Okay? Markov property at time 1. Okay, but what this tells you, look, if you think of this as a function of this point, okay, then, so if you define a function, I don't know, g little y here of x, if you define this to be g x y, so you fix your y and you just look at it as a function of x, then what we proved here, I minus p on my function, right, this is acting on this coordinate, is exactly delta. So we proved that delta, the Laplacian of gy is delta y. This is the solution to the Dirichlet problem.
This is something we do.
Yes. This is the solution to the Dirichlet problem. Okay? What this tells you, okay, what this tells you is something about the psi's. Because the psi, so in a sense, g is a kind of inverse, the green function is a kind of inverse to the Laplacian. Okay? Or if you want, if I apply the Laplacian to psi n, what is this? Let's see what this is, right? This is the Laplacian applied to g, right? You have to be careful because, yeah, so, yeah, so, okay, so how do we, okay, yeah, so if the Laplacian of psi n at a point, what is this? This is, right, this is some number, which is what? It's the sum over all y of this function, right, with a coefficient f and y, right? So, sorry, so this is this. This is f and y, this number times this function. So this is an equality of functions, just by definition, right? So when I apply the Laplacian to this guy, okay, what I get is I apply, these are coefficients, it's a linear operator, I bring the Laplacian inside, right? What I get is the sum over all y, f and y, delta, delta y of this, right? Okay? So Laplacian psi n of x is what? It's just fn of x. This is the green function, why the green function is a kind of inverse. If I want to solve Laplacian psi n equals fn, then the solution is psi n equals gfn. Okay? But now I want you to notice something. What is Laplacian psi n, psi n? Well, by what we just said, this is fn g fn. Right? This is the sum. Maybe I don't want to do gfn. I want to go back to this representation. Okay, this is psi n of x, right? Expected number of time random walk sponge of x. So I could write here. So this is f. The first one is fn. The second one is psi n. I leave the psi n, right? And I sum over all the x's, right? What is inner product? Just sum over all the x's, right? This times this. So I have everything is real valued. I started and right. There's no complex conjugates. So I have the sum over x's. This is fn of x. So this just tells me you have to take x from fn. And then you have the expected number of times you visit fn started from x. This is this one at x. Which is what? This is just, I can write it shorthand, gfn fn. Right? This means sum both coordinates. Right? It's what you should think about is that this is start uniformly in Fn and count the number of visits you make to Fn. And then this is f, the size of Fn times what I just said. Okay?
The size of Fn
times the uniform distribution starting at Fn. How many times do you visit Fn in an expectation? Okay? So this is some quantity. Okay? It's non-zero. Okay? And now what is, on the other hand, what is Laplacian psi n norm squared or with itself, right? Well, Laplacian psi n is Fn. So this is what? This is the sum over all x, Fn x squared, which is just the size of Fn. So what is Laplacian psi n norm squared divided, remember this is what we wanted, to go to 0, right? What is this thing? עזבת ברגע קריטי. This is what? This is exactly 1 divided by, start uniformly in Fn, right? And let me even write it clear, and ask for the expected number of visits to Fn. Start uniformly in Fn and ask for the expected number of visits to Fn. This, I want to go to 0. And it's an exercise to prove that for a Fellner set, this always goes to 0. For a sequence of Fellner sets, this goes to 0. Okay?
And it goes to infinity.
Yes. The expected. Why? Because Fellner sets have small boundary. So if you start uniformly in a Fellner set, so you have a Fellner set, which I like to draw as squares. Okay? You have a Fellner set, you have a small boundary compared to the volume. You start uniformly. Okay? How many times do you visit Fn? Well, you visit basically, right, you start walking around until you exit, right? So you have to somehow start far away from the boundary. Now, kind of if you take, say, maybe half the Fellner set or something like that, right, then you kind of have a reasonable chance, say probability 1% to fall in that set. But then you have a while to walk here, to get out. Okay? So the number of visits will go to infinity. Expected number of visits will be at least this probability of falling far away from the boundary. And because the boundary is very small, falling close to the boundary is negligible. It's going to 0. Okay? Yeah. And that's exactly the property of Fellner sets. You have small boundaries. Okay, so need to prove this statement, but let's give it as an exercise. If Fn is a Fellner sequence, then 1 over Fn G Fn goes to infinity. Okay? Okay, so that was the construction, but I cheated. Where did I cheat? זה רק אתה אז.
אני גם אמור לעזור. משהו בבית ולא אמור.
Okay, so there are 2 important places where I cheated and that I have to be careful, and this is why next lesson we're going to do something more complicated, but it's really just capturing this idea. It's really this simple idea. You take an indicator and you do a Fellner set. That's all. And you take an indicator of a Fellner set and you take the green function. You want the solution to Laplacian phi equals the indicator of a Fellner set. That's all you want. And I cheated in 2 places. One is that does the green function even converge? That's only if the walk is transient. I mean, so definitely there are some groups for which this doesn't converge. Okay. Okay. So that's one problem. And even if it does converge, that doesn't mean that if I apply it to an L0, to a finitely supported function, that this is in L2. Remember, the whole thing worked only if the psi's were in L2. I needed to do inner products, I needed to do things. These two things, and this is even worse. Okay? Because the fact that, so this is equivalent, the fact that G will take L0 into L2, okay? This is equivalent to this, sum G, X, Y, not just that G, X, Y exists, but rather that if you take the sum of the squares of G of X, Y, this is finite. Okay? It's equivalent. You can check why it's equivalent. I mean, it's easy to see that it's equivalent. Basically, it's this. But, okay? So, this is called the bubble condition sometimes. This comes from somewhere else. Bubble conditions comes from self-avoiding walks, speculation, things like that. It doesn't have to do any, well, it does have to do something with random walks, but, and this happens, so this happens if the dimension, let me write, so this is true if the dimension, which I didn't say what that is, of G, is bigger than 4. Strictly bigger than 4. Okay, then it will happen. It's equivalent to saying that two independent random walks do not meet with positive probability. So they start from the origin, but they don't meet again with some positive probability. You see, that's stronger than transients, right? Transient says you don't return to the origin with positive probability. Here it's like if you just take two independent random walks, they never will meet each other with positive probability. So this is a stronger condition. You need higher dimension for that to work. This whole construction is good. I mean, we could have thrown away the small dimensional groups and maybe analyzed them separately somehow, but we'll see how to get around this game of, what we'll just do is instead of taking GF, which we cannot, we have F of finite support, what we'll do is we'll look at the following. So G would be to take the infinite sum. What we'll do is we'll truncate the sum, right? G was to apply the infinite sum to F. Instead of that, we'll apply this finite sum of the powers of P to F, take an average, and then we take a limit of this thing. So we can kind of call this our new G, or this will be, the limit of these things will be our psi. Yes, so that's zero mean, right? And so this psi will be the limit of these things. Now you have to start proving what, you have to start proving all the things that we take for granted, like what is the Laplacian of psi. Okay? So this does converge in L2, right? Because if you apply a P to a power of P to a L0 function, you get an L2 function. That's always the case. You can show that P is a contraction on L2. And so this works. And this zero mean converges in L2 because L2 is complete and everything is nice. And then you want to say, what is the Laplacian of psi? Right? Then you will get back that the Laplacian of psi is something like that, and so you can work. But you have to be careful with these things, okay? You have to be careful. Now you have to do it properly and, work with these means instead of them, which makes things technically more complicated.
We are going to do next thing.
Yeah, that's what we'll do next week to prove it properly. Okay.
Okay.